In the last video we looked at spanning sets, and so we saw some very common spanning sets that we can create. In 3-space we showed the spanning set I, J, K, I being the vector 1, 0, 0, J being 0, 1, 0, and K being 0, 0, 1. Those vectors indeed spanned, we say, 3-space. In other words, every ordered triple can be written as a linear combination of those three vectors. So how do we, and that's not the only spanning set though, how do we determine whether a set spans a particular vector space or subspace? Well, I'm going to show you how to do that now with this example. So these three vectors here, v1, v2, and v3, do they span all of 3-space? Okay, what do we mean by that, spanning all 3-space? That means for any vector in 3-space, let's call the vector b, and we'll just say b is b1, b2, b3. Let that be in 3-space. For any, I said and, for any vector b, do there exist scalars, and let's call these scalars, I don't know, k1, k2, and k3, because we've got three vectors up there, so I need three scalars, such that k1 times v1 plus k2 times v2 plus k3 times v3 equals b. Is b a linear combination of those three vectors? So if we could do that for any, right, for any arbitrary vector in 3-space, we can find three such scalars, then the answer would be yes, these vectors do span 3-space. Okay. Well, let's see, what does this equation look like? What does this equation look like? Well, I've got k1 times v1. What's k1 times v1? Here's v1. If I scalar multiply that by k1, what do I get? I get 3k1, 1 times k1, 2 times k1. Right? I just scalar multiply every component. v2, what's k2 times v2? So I'm going to add that. I'm going to have k2 times 1, negative k2, and k2. And then plus k3 v3. And what's b? b1, b2, b3. And space there. b1, b2, b3. That's the vector b. And so, what do we have here? I mean, how are we going to solve? How are we going to determine whether we have these scalars? Well, this should look familiar to you when we were talking about vectors back in n-space and 3-space. We talked about, can I write a particular vector as a linear combination of given vectors? Now this is an arbitrary vector, so we're going to talk about that. But we basically set up a system of linear equations because, right, if I combine, right, these three vectors, I'm going to combine by adding, right, the corresponding components. So 3k1 plus k2 plus 3k3, what does that have to equal? It has to equal the first component here, which is b1. Right? And then the second component is k1 plus a negative k2 or minus k2 plus 5k3, b2. And then the last component is 2k1 plus k2 plus k3 equals b3. And we have what? It's a system of linear equations, right? But these are not, these are arbitrary. If these were known values, 1, 7, 8, or whatever, we would be able to solve that system. Okay. I'm going to represent this system as ax equal b. Right? And what's a? A is the coefficient matrix. Let's take a look at that coefficient matrix here in this case. It's going to be what? 3, 1, 2, 1, negative 1, 1, 3, 5, 1. Right. So what's our real question though? Go back to our question. We're trying to say, do there exist these scalars for any such b, for any such b? So for any possible combinations of any three real numbers I can put here, is there what? A solution to the system. What do we call such a system? Consistent, right? And so what we really want to know is for what values of b is this system consistent? But this should ring a bell. Our coefficient matrix A in this case is square. And for square matrices, we have some conditions to know when the system AX equal B is consistent. In fact, this system, AX equal B, is consistent for every 3x1 vector B. Does that sound familiar language? Where's this language come from? This system is consistent for every 3x1 vector B if and only if, that's my abbreviation right there for if and only if, what? A is what? Invertible. Remember the list of equivalent statements, right? To A being invertible, one of the statements was the system AX equal B is consistent for every 3x1 vector B. In this case, we have 3x3 matrix. But this is true if and only if what? There's several statements, and one that's very easy to use is what? The determinant of A is what? If A is invertible, the determinant of A is what? Not equal to 0. So look, I can tell if this system is consistent for every vector B by simply looking at the determinant. If the determinant of this matrix is not 0, then this system is consistent. What happens if the determinant is equal to 0? Well, that means there's at least one B where this system is not consistent. In that case, right, would we be able to, for any B, write this as a linear combination with these scalars? No. Right, there would be at least one B where we could not do it. And in fact, I'll let you go ahead and do this. So if you actually go with your calculator, you can compute the determinant. And the determinant of A is equal to 0 in this case. Uh-oh, what's that mean? Equal to 0. Well, A is not invertible. And it means the system is inconsistent for at least one B. And so we can now go and answer the question, right? Since the determinant is 0, there's one combination of B1, B2, and B3 here where this system would not be consistent. We would not have any solution. We would not have values of K1, K2, and K3. So I could not write, going back to the original question, I could not write that particular B as a linear combination of the vectors of B. So do the vectors span 3-space? No. So make sure we answer the question again, right, based on the analysis below. Now, what can happen down here differently? Certainly, if we got the determinant of A not to be 0, our answer would be yes, right? We would be able to solve this system for any such B. But also we can have a system where the coefficient matrix A is not square. What are we going to have to do there? Well, that's going to be a little bit bothersome, and until we do a little bit more analysis, we'll hold off on that question for the time being, because being able, solving a system where these guys are unknown, so to speak, or can vary, our variables, it gets a little messy. Okay, but we'll be able to clean that up a little bit as we talk more about these topics. Okay. A quick little theorem here now. It's about a particular subspace. We want to prove that the solution set of a homogeneous linear system, AX equals 0, of m equations and n unknowns is a subspace of n space. Okay, so what in the world is this all about? So homogeneous, remember, means what? The homogeneous part means that the constants are all what? 0. That's the important thing, right? From this. Now, if we have m equations and n unknowns, then I'll have you note that the matrix A must be m by n. So what does the vector x have to be in order for this multiplication to work? Remember, number of columns here has to match the number of rows here. So x has to be n by 1. And x is, that's our unknowns in this equation. What are the unknowns? X, right? N unknowns, right? And notice it's an n tuple. So it's certainly a subset of n space, but we're saying that the set of all possible x, right, n tuples here, is actually a subspace. So how do we prove that? What are the two things we have to prove for a subspace? What are they? You should know them by now. What are they? Number 1, closure under addition. Number 2, closure under scalar multiplication. So let's suppose we have two solutions. We'll call these x sub 1 and x sub 2. Let x1 actually be solutions to ax equals 0. Right. Those are the vectors that we have here. These are n tuples. The 0 vector, by the way, is an m by 1, right? Because when I multiply these two together, I get m by 1. But x is n by 1, so is x1, x2. So, okay. So again, this is, we're saying they're basically in the set of all the solution set. So what do we know then? What do we know? Again, we always have to base on what we know. Well, thus, if that's the case, a times x1 must be the 0 vector, and a times x2 must be the 0 vector, because they're solutions. Right? That must be true. So, what do we need to do? Closure. If these are both solutions, is x1 plus x2 in this solution set? Is this a solution? Well, I'm going to check. What I'm going to do is I'm going to take A and multiply it by this vector, which is the sum of these two vectors, and see if it's a solution. What do I have to get it to be a solution? I have to get the 0 vector. Well, we do have a distributive property, in this case, distributing on the left, A over the sum. Right. But what's A times x1? It's the 0 vector. What's A times x2? It's the 0 vector. Add those together, we get the 0 vector. So this here, right, tells me what? Yes. Right? Yes. Right. Closed, we're closed under addition. So I've taken two arbitrary solutions, added them together, and I get a solution. What else do we have to show? Closure under scalar multiplication. So is for any arbitrary scalar k, is k times x1 a solution? Again, pretty easy to show. I'm going to take a times, right? And here's the thing about scalars. Scalars, right, they can come out anywhere in our matrix multiplication. I can pull it out in front, right? And then I've got this, same thing, right? But what's a times x1? That's the 0 vector. What's the scalar multiple of any 0 vector? 0 vector. And so this information here tells me yes. And this means what? We're closed under scalar multiplication. And that's the proof. That's what we had to show. Now, we're going to talk more about this we're going to talk quite a lot about this subspace. And later on, we're going to call this actually the null space of the matrix A. But we'll talk about that later on in chapter 4. But this is a very important one. Being able to find this particular solution set and describe it is something that you started from the beginning, because you're just solving a system of linear equations. You just solve this system. solve this system. And remember, what can we have? You can have, well, we have to have a consistent, it's consistent, right? We always have the trivial solution. So you're not going to come up with no solution. You're going to have what? The trivial solution only, right? Which would be what? The zero subspace. Or you'll have infinitely many solutions, including the zero vector. And so, and you can, if you have a particular system, you can, and we'll do an example, you can parameterize. Now, we did talk a while back, if you remember, about matrix transformations, and we'll come back to this a little bit later, but if we have a matrix transformation from n space to m space, then the solution space of AX equals 0 is the set of all vectors in n space that this transformation maps into the 0 vector in m space. So multiplication by the matrix A, right, any n tuple, if it gives us the 0 vector, then the set of all such vectors is called the kernel of the transformation. So the kernel is the name we give this set in this case. And so this is just saying the same thing, we're just renaming it. When we're talking about matrix transformations, we use the term kernel. If we're talking about the matrix itself, we'll see later on, we talk about the null space. If we're talking about the systems of linear equations, we're just talking about the solution space, or solution, we call it solution space now, since it's a subspace of AX equals 0. Okay, so let's just close with, actually do an example. Let's find the kernel, or the solution space, for a given matrix transformation. Do you remember matrix transformations? Here's an example. This is a matrix transformation from 3 space to 2 space. Notice the inputs are what? Ordered triples. They reside in 3 space. The output is what? Look at the comma there. We have ordered pair. It's in 2 space. Okay. So, do you remember how to come up with the standard matrix for this transformation? If I call this W1 and I call this W2, look at this, we have W1 is x1 plus 2x2 plus x3, and W2 is 3x1 plus 8x2. And this is a system of linear equations. I can describe this as W equals AX, right? Where what is W? W is just the 2x1 output, W1, W2. X is the 3x1 input, X1, X2, X3. And A is what? Our coefficient matrix, which is, notice, going to be 2x3. 1, 2, 1, pulling off the coefficients here. 3, 8, 0. So if I multiply A times X, right, I get this. And then W is equal to that. So that's the matrix equation for that. So the kernel of the matrix transformation, what is that going to be? This is all vectors X in 3 space, which is our domain, right, where we're mapping from, such that T of X equals 0, the output equals the 0 vector. And this T of X, what is that? Well, that's just nothing more than matrix multiplication, A times X. So, in other words, we're just solving the system AX equals 0, where A is this matrix. So how do we solve AX equals 0? Well, go back to the good old days, right? We're going to look at the augmented matrix, which is what? A is 1, 2, 1, 3, 8, 0, and then we add on what? The constants, right? The constants go here. So again, this is the A, and these are the constants, right? That's our augmented matrix. What do we do with that? Gaussian elimination, right? Or Gauss-Jordan elimination. Put it in reduced row echelon form. We do all the row operations, right? We got a 1 here. We multiply first row by -3, add it to row 2, get a 0 here, and so on, right? We're not going to do all those steps now, right? We hopefully know how to do that, but we're going to use technology, right? We're going to use the calculator's RREF command, and we get this. I'm going to use the convert to fraction command. Remember, convert to fraction command will be helpful. And remember, we have three unknowns, x1, x2, and x3. Notice I have leading ones in x1 and x2. So what's that mean about x3? x3 is a parameter, a free variable, because it has no leading one there. And so we're going to let x3 be something like t. So what does the first equation say? x1 plus 0x2 plus 4x3 equals 0. And so I can solve for my fixed variable x of 1 in terms of x of 3 or t. X of 1 is what? Subtracting negative 4t. Second equation says x of 2 minus 3 halves x of 3 equals 0. And I can solve for x of 2 by adding 3 halves x of 3 or t. And so putting this all together, what is the set of all x that satisfies ax equals 0? Well, x1 is negative 4t, x2 is, oops, that should be equal sign there, sorry, equal, 3 halves t, and x3 is t. Notice this is the same as t times negative 4, 3 halves, 1. That's something we'll get into. So here's the kernel. The kernel of this t sub a is a set of all vectors such that t is any real number. And I like to put it in this form because it's basically all scalar multiples of this one vector. And if you think about it, this one vector then spans the entire set. This one vector spans any scalar multiple. You know, t could be 0, we get the 0 vector, or t can be 1, t can be negative 1, t can be any real number, and we'll get all these vectors. This forms a subspace of 3 space. And I'll let you think about it. We're going to close this video out, but I'll let you think about it. This set, if you think about it geometrically in 3 space, which we can, this represents a line passing through the origin. And if you remember, one of the possible subspaces of 3 space was a line passing through the origin. So we're going to do a lot more analysis now in vector spaces and subspaces in the coming chapters, but this is the end of our introduction then to subspaces.